If you run Postgres in production, this is the single most important video you can watch. Vacuum is not a maintenance command. Vacuum is the subsystem that decides whether your database keeps running or falls over. Over the next 22 slides, we are going to trace exactly what happens inside Postgres when you run an update or a delete. You will see why nothing actually gets deleted, why your tables keep growing anyway, and why ignoring vacuum is one of the most common ways production Postgres databases die. I am going to show you the internals, the tuning knobs that actually matter, real production disasters from companies you know, and the 8 signals you need on your monitoring dashboard. By the end of this video, you will not just know what vacuum does. You will know how to tune it, how to debug it, and how to spot the failure modes before they take you down. Let us start at the beginning. Here is the single most important thing to understand about Postgres. It never updates a row in place. Never. When you run an update, Postgres does not overwrite the existing row. It writes a brand new version of the row, and marks the old version as obsolete. Both versions live on disk at the same time. Different concurrent transactions see different versions, depending on when they started. This is called multi-version concurrency control, or MVCC. And it is a deliberate trade. What you get from MVCC is huge. Readers never block writers. Writers never block readers. Every transaction sees a consistent snapshot of the database, without taking a single lock. That is the property that lets you run heavy analytics against a busy OLTP system without bringing it to its knees. But the trade is not free. Every update leaves an obsolete row version behind. Every delete leaves the deleted row physically present on disk, just marked as no longer visible. These obsolete row versions are called dead tuples. And they pile up. Vacuum is the garbage collector that cleans them. Skip vacuum, and 3 things happen, in order. First, your tables grow even though row counts stay constant. Second, queries get slower because every scan reads dead bytes. Third, eventually, the database refuses all writes. That third one has taken down Sentry, MailChimp, GoCardless, and many others. We are going to cover all 3 failure modes in detail. Keep watching. Every row in Postgres carries hidden bookkeeping fields. They are invisible in normal selects. But they are the engine of MVCC. And once you can see them, MVCC stops being magic. The 2 most important are SMIN and SMAX. SMIN stores the transaction ID that created this version of the row. SMAX stores the transaction ID that deleted or updated it. Or 0, if the row is still alive. There are other fields too. TID is the physical location of the row, expressed as a block number and offset. That is what indexes point to. T_infomask holds visibility hint bits. Whether the creator committed, whether the row is frozen, whether this is a heap-only tuple, and so on. The visibility rule is simple. A tuple is visible to your transaction if it's SMIN committed before your snapshot started. And either its SMAX is 0, or the deleter committed after your snapshot, or the deleter rolled back. That is the entire game. Every select in Postgres runs that comparison against every tuple it considers. You can see all of this directly. Just select SMIN, SMAX, TID, and your real columns. Try it. Once you can see the bookkeeping, everything that follows in this video makes sense. Let us walk through a real example. 2 sessions, 1 row, 2 different truths. Session A begins a transaction at transaction ID 100. It reads a row from the orders table. The row has SMIN equal to 98, SMAX equal to 0. Session A sees the row with total of 49.99. Now session B begins at transaction ID 102. It updates the same row, sets total to 59.99, and commits. What happened on disk? The original row had its SMAX stamped with 102. A brand new tuple was written, with SMIN 102 and total 5999. Two versions, same row, both physically present. Session A reads the row again. Still sees 4999. Why? Because Session A's snapshot was taken at XID 100. The new version has SMIN 102. That is in the future from Session A's perspective. So Session A correctly sees the old version. Session B sees the new version. Neither blocked the other. Neither took a row lock. This is MVCC working exactly as designed. And the moment Session A commits, the original row becomes a dead tuple. But it cannot be cleaned up yet. Some other long-running transaction might still need it. Hold on to that thought. We will come back to it. Now let us watch bloat appear in real time. For operations on a single 8 kilobyte heap page. Step 1. Initial state. 8 live rows on the page. Clean and tight. Step 2. We run an update on row 3. The update does not modify the row in place. The original row 3 has its SMAC stamped with the updating transaction's ID. That marks it dead. A brand new version of row 3 is written into the next available slot. We now have one dead tuple plus a new live tuple. The page is fuller. The visible row count is the same. Step 3. We delete rows 5 and 7. Critically, the delete removes nothing physically. It just stamps the SMAX field on those two rows. From the application's perspective, those rows are gone. They fail the visibility rule. From the disk's perspective, they are still there, taking up the same space. We now have 3 dead tuples on this page. Step 4. The result. 7 live tuples. 3 dead tuples. 30% of the page wasted on rows nobody can see. After just 4 operations. Now scale it up. A table taking 1 million updates per day grows continuously, even if its row count stays perfectly constant. Every query, every index scan, every sequential read, every join, all of them pay for the bloat. Without vacuum, this never stops. The table just keeps growing. This is the problem. Now let us see the fix. Plain vacuum runs in 3 logical phases. Watch what it does. Phase 1. Identify dead tuples. For every tuple in every page, vacuum checks if its SMAX is older than the global SMIN horizon. The horizon is the oldest active transaction snapshot. If the dead tuple is older than that, no transaction will ever need it again. It is safe to remove. Phase 2. Reclaim space. Vacuum marks the dead tuple slots as reusable in the page's free space map. Future inserts can reclaim those slots. But the file size on disk does not change. Phase 3. Clean indexes. Vacuum walks every index and removes index entries that pointed to those dead tuples. Otherwise, future lookups would waste effort following dead pointers. Now, what plain vacuum deliberately does not do is just as important. It does not shrink the file. It does not defragment. And it does not block reads or writes. It only takes a share update exclusive lock, which is compatible with normal queries. Think of plain vacuum as garbage collection inside a fixed size building. Not knocking down walls. It returns space to the table, not to the operating system. A table you vacuumed yesterday can still look huge on disk today, and that is working as intended. The free space inside the file gets reused by future writes. Now, what if you actually want to shrink the file? That is a totally different command. And it is dangerous. If you remember nothing else from this video, remember this slide. Plain vacuum and vacuum full sound similar. They share a name. They are profoundly different. Confusing them is how engineers take production down at 3 in the morning. Plain vacuum is online. It only takes a share update exclusive lock, so concurrent reads and writes proceed normally. It marks dead tuple slots as reusable. The file size on disk does not change. It is incremental, can be paused and resumed, and is what Autovacuum runs in the background. It is safe to run anytime, on any table, under any load. Vacuum full is the opposite. It takes an access exclusive lock on the table. While it runs, no query can read or write that table. Every connection that touches it blocks until vacuum full finishes. It rewrites the entire table into a brand new file, then drops the old one. The disk size shrinks. But it requires up to twice the table's size in free disk during the rewrite. And on big tables, it takes hours. Look at this table. A 1 GB table takes about 30 seconds. 50 GB takes 20 minutes. 500 GB takes about 3 hours of total downtime. 5 TB is days. Vacuum full on a hot production table during business hours is a career-ending command. The production answer is almost always not vacuum full. It is PG_repack, an extension that rewrites tables online. It only holds an exclusive lot briefly at the very start and very end of the operation. It reclaims space the same way vacuum full does, without the multi-hour outage. Use PG_repack 99% of the time when you actually need to shrink a bloated table. Reserve vacuum full for emergency situations only. Why does vacuum get faster after the first run? Why are some queries 100 times faster than they should be? Both answers live in one tiny file called the visibility map. Every table has a companion visibility map, or VM. It is a bitmap. 2 bits per heap page. The first bit, all visible, says every tuple on this page is visible to every active transaction. Vacuum can skip it. The second bit, all frozen, says every tuple has been frozen against transaction ID wraparound. Anti-wraparound vacuum can skip it too. The visibility map is the reason vacuum does not get linearly slower as your table grows. A table that is mostly read-only gets vacuumed in seconds, even at terabyte scale. Because vacuum walks only the pages that have changed since the last run. The visibility map turns vacuum from a problem proportional to total table size into a problem proportional to changed pages. The other big payoff is index-only scans. If your query only needs columns that exist in the index, and the heap page is marked all visible, Postgres can answer the query without ever touching the heap. That is a massive speedup for read-heavy workloads. When you see a high heap fetches number in Explain, that means your visibility map is stale. Many of your heap pages are not marked all visible. Running vacuum will fix it. This is also why running analyze alone is not enough. You need vacuum to refresh the visibility map. You almost never run vacuum by hand in production. A background daemon called Autovacuum does it for you. But here is the catch. Only if you tune it correctly. The defaults in PostgreSQL.conf are calibrated for 15-year-old hardware. They are conservative to a fault on modern systems. The trigger formula is straightforward. For each table, Autovacuum computes a threshold. The threshold equals Autovacuum_vacuum_threshold plus the scale factor times the number of live tuples. The defaults are 50 for the threshold and 0.2 for the scale factor. So a table with 10,000 rows gets vacuumed at about 2,000 dead tuples. Reasonable. A table with 1 million rows? 200,000 dead tuples before vacuum kicks in. A table with 100 million rows? 20 million dead tuples. By the time Autovacuum decides to run on a billion-row table, you are 200 million dead tuples deep. That is a disaster. Autovacuum has 3 jobs. Reclaim space, by running plain vacuum when dead tuples cross the threshold. Update statistics, by running analyze so the query planner has accurate row counts. And prevent transaction ID wraparound, which we are going to cover in detail on the next slide. The single most impactful tuning change for any large table is lowering the scale factor per table. Alter table my underscore table set autovacuum underscore vacuum underscore scale underscore factor equals 0.02. That tells Postgres to vacuum every 2% of churn instead of every 20%. On a hot billion row table, that is the difference between vacuums every 20 minutes and vacuums never finishing. Now we get to the failure mode that turns vacuum from a performance topic into infrastructure. This is the one that takes databases down. Transaction IDs in Postgres are 32-bit integers. About 4.3 billion values total. Allocated sequentially. Once you use them all, you wrap back to zero. Here is the problem. The visibility logic compares transaction IDs not as absolute numbers, but as relative ages on a circular axis. Anything more than 2 billion XIDs in the past is treated as in the future. Now imagine a row created at XID 100, decades ago. The counter wraps all the way around. We are back to XID 100. Suddenly that ancient row looks like it was created in the future. It becomes invisible to every transaction. Silent. Data. Loss. This would be catastrophic. So Postgres has a defense. Freezing. Vacuum periodically freezes old tuples. Freezing replaces a tuple SMIN with a special frozen XID marker. That marker is interpreted as older than every possible transaction. A frozen tuple is immune to wraparound forever. But freezing only works if vacuum runs. So what happens if vacuum falls behind? Watch this timeline. At 200 million XIDs old, Autovacuum freeze max age is reached. Postgres triggers an aggressive anti-wraparound vacuum, even on tables you told it to ignore. At about 2 billion XIDs, your logs start screaming. Database must be vacuumed within n transactions. At about 2 billion, 140 million, the database refuses all writes. You drop into single user mode and run vacuum freeze manually. This has happened publicly to Sentry, to MailChimp, to Go Cardless, to Joyent. It happens privately to dozens of others every year. The lesson is simple. Monitor age of dat frozenxit every single day. Act long before it crosses 1 billion. This is non-negotiable. Autovacuum is running. The dead tuple count keeps climbing. The on-call engineer says vacuum is broken. Almost always, vacuum is fine. The SMIN horizon is being held back. This is the single most common real-world reason vacuum appears to fail in production. Vacuum cannot remove a dead tuple if any active transaction snapshot might still need it. The oldest such snapshot defines the SMIN horizon. Anything newer than the horizon is untouchable. No matter how dead it is. The horizon is global to the database. One stuck transaction blocks vacuum on every table. What holds the horizon back? 5 things, in roughly decreasing order of frequency. Number 1. Idle in transaction connections. The application opened a transaction, ran a query, and forgot to commit. Maybe a code path returned early. Maybe a connection pool returned an unclean connection. The transaction sits there for hours. Number 2. Inactive logical replication slots. A subscriber went offline 3 days ago and nobody noticed. The slot is silently accumulating unvacuumable bloat on the publisher. Number 3. Legitimately long-running queries. Analytic jobs, BI tools, data exports. Not bugs, but they have the same effect on vacuum. Number 4. Prepared transactions. The two-phase commit kind. A failed XA coordinator can leave one in PG_prepared_X that holds the horizon literally forever. Even surviving server restarts. Number 5. Hot standby feedback equals on. This tells the primary to delay vacuum based on the standby snapshots. Useful, but if the standby has long queries, they hold the primary's horizon. The query you must memorize is on screen. It tells you who is holding the horizon back. Kill it, drop the slot, or commit the prepared transaction, and vacuum will catch up. Set up alerts on transactions open longer than 5 minutes, and inactive replication slots. That single discipline prevents most vacuum incidents. Not every update creates index bloat. Heap-only tuples, also known as hot updates, are PostgreSQL's quiet superpower. Most teams completely miss them. An update qualifies as hot if two conditions are both met. First, none of the indexed columns changed. Second, the new row version fits on the same page as the old one. When both hold, Postgres performs a remarkable optimization. It does not update any index. The new tuple is chained to the old one inside the same page. Index lookups still find the row by walking the chain. Why does this matter? Imagine a table with 8 indexes. Without hot, every single update touches every single index. 8 times the right amplification. 8 sources of index bloat. With hot, those 8 indexes are completely untouched. And there is a second magic. Hot chains can be cleaned up by a lighter mechanism called hot pruning. It runs opportunistically during normal selects and updates. No full vacuum needed. How do you encourage hot updates? 3 things. First, do not index volatile columns. If last_seen_at gets updated on every request, indexing it kills hot for every update. Second, lower fill factor on update-heavy tables. Alter table X set fill factor equals 80. Pages start 80% full instead of 100. That leaves room for new versions on the same page. This single change can be transformative. Third, monitor n_tup_hot_upt in pg_stat_user_tables. The count of hot updates. Aim for a hot update ratio above 0.8 on your hot tables. If it is below 0.5, something in your schema is preventing hot. Finding it is high leverage work. You cannot fix what you cannot see. These are the queries every Postgres operator should have memorized. The fastest health check is pg_stat_user_tables. Select rel name, n_live_tup, n_dead_tup, the dead tuple ratio, the total relation size, and the timestamps of last_Autovacuum. Order by n_dead_tup descending, limit 20. Run it weekly. That single query surfaces 90% of bloat issues. When you need exact numbers, use the pgstatuple extension. It reads every page and gives you exact counts. Tuple count, dead tuple count, free space, percentage bloat. It is slow because it reads the entire table. There is also pgstatuple_approx, which samples pages and is much faster. Accurate enough for most diagnostics. Index bloat is often worse than table bloat. And vacuum does not shrink indexes. It only removes individual entries. Use pg_stat_user_indexes joined with pg_relation_size to find indexes that are huge relative to their row count. The fix for a bloated index is re-index concurrently. It rebuilds the index without blocking writes. And finally, watch a vacuum in real time using pg_stat_progress_vacuum. It tells you the phase. Scanning heap, vacuuming indexes, vacuuming heap, cleaning up indexes, truncating heap. And how many pages have been processed? Invaluable when a vacuum seems stuck. Memorize these queries. They are your debugging vocabulary. There are over 30 Autovacuum related parameters. A handful do 90% of the work. Tuning the wrong ones is wasted effort. Tuning these is transformative. The single most impactful is Autovacuum_vacuum_scale_factor. The default 0.2 is fine for tiny tables. Disastrous for large ones. Lower it to between 0.02 and 0.05 per table on your big tables. Next, Autovacuum cost limit. This is Vacuum's input-output budget per cycle. How much work it can do before pausing. The default of 200 is throttled for spinning disks. On modern SSDs, set it to 2000 or 4000. Then Autovacuum nap time. How often the launcher wakes up. Default 1 minute. On a system with many busy tables, lower this to 15 seconds. Autovacuum max workers controls concurrent vacuum jobs. Default 3. On modern multi-core systems with many active tables, raise it to 5 or 10. Autovacuum freeze max age controls when forced anti-wraparound vacuum kicks in. Default 200 million. On busy systems, lower it to 100 million. That spreads the freezing work over time, instead of letting it all hit at once. Finally, maintenance work MEM. The memory budget per vacuum worker for storing the dead tuple list. The default 64 megabytes is laughably small for big tables. When vacuum runs out of memory, it has to do multiple passes over the indexes. The same work, multiple times. Raise it to 512 megabytes or even 2 gigabytes. The starter profile on the slide is a sensible production baseline. The order of operations is: first, lower scale factor. Then raise cost limit. Then raise maintenance work MEM. Then add workers. Stop after that unless monitoring shows specific issues. Resist the urge to tune everything. Even with Autovacuum tuned beautifully, certain workload patterns leave bloat untouched. These are the production landmines. Every Postgres operator should know all of them by name. Number 1. Long-running transactions. We covered this on the SMIN horizon slide. An idle in-transaction connection holds the horizon for the entire database. One stuck transaction can disable vacuum globally. Number 2. Inactive replication slots. A subscriber offline for a week silently accumulates a week of unvacuumable bloat. This is the worst landmine because it is invisible from inside the database. The vacuum statistics look normal. The dead tuple count just keeps climbing. Number 3. Lock contention. Autovacuum is polite. It yields to user queries that conflict with it. Heavy DDL or batch jobs that constantly grab the table cause vacuum to back off and never finish. Look in the Autovacuum log for the phrase aborting due to lock conflict. Number 4. Cost limit starvation. The default cost limit pauses vacuum every few thousand pages. On a heavily written table, vacuum falls behind faster than it cleans. Looks like vacuum is not working. Actually, vacuum is running, just throttled below the rate of new dead tuples. Number 5. Prepared transactions left behind by a failed XA coordinator. They live in PG_prepared_Zax and hold the horizon literally forever, surviving server restarts. Number 6. Hot standby feedback equals on. Useful when you want to prevent query cancellation on the standby. But if the standby has long queries, they hold the primary's horizon. Each of these patterns has a specific diagnostic query and a specific fix. Have them in your runbook before you need them. 2 a.m. The on-call alert fires. Table is bloated. You need to triage in under 5 minutes. Use this decision tree. Step 1. Confirm the bloat is real. Query pg_stat_user_tables for the table. Look at n_live_tup, n_dead_tup, and last_autovacuum. If the dead tuple ratio is over 20%, the alert is real. If not, run analyze and recheck. Step 2. Is Autovacuum currently running on this table? Check pg_stat_progress_vacuum. If yes, vacuum is running but slow. Go to step 4. If no one last_Autovacuum is hours old, Autovacuum is being prevented from running. Go to step 3. Step 3. Is something blocking the SMIN horizon? Run the query from slide 11. Check pg_stat_activity for the oldest backend SMIN. Check pg_replication_slots for inactive slots. Check pg_prepared_zax for stuck two-phase commits. Find the offender. Kill it, drop it, or roll it back. Then rerun vacuum. Step 4. Vacuum is running but slow. Look at the phase column in pg_stat_progress_vacuum. Stuck on scanning heap means cost limit is too low. Set vacuum_cost_limit equals 4000 and run vacuum manually. Repeating vacuuming indexes phase means maintenance_work_mem is too small. The dead tuple list does not fit. Raise it. Truncating heap phase means vacuum is waiting for access exclusive lock at the end. Usually harmless. Step 5. Manual rescue. Set vacuum_cost_limit to 10,000. Set maintenance_work_mem to 2 GB. Run vacuum with verbose and analyze. If the bloat is in indexes, re-index concurrently. If the table is irrecoverably bloated and you have a maintenance window, use pg_repack. Never vacuum full on a hot production table. This decision tree handles 95% of vacuum incidents. Print it. Tape it to your monitor. Use it. Theory is fine. The lessons stick when you see vacuum takedown companies you have heard of. Sentry. 2015. Their database refused all rights. The site went down. The cause was transaction ID wraparound. Autovacuum had been silently failing for weeks because of a misbehaving extension that was holding the SMIN horizon. Their fix was single user mode vacuum freeze. 12 hours of total downtime. The lesson. Monitor age of datfrozanxid, not just dead tuple counts. The wraparound clock is invisible to most dashboards. MailChimp. 2019. Symptom. Replication broken, primary slowing down. The cause was an inactive logical replication slot that had accumulated 800 GB of write-ahead log. Vacuum could not run because the slot was holding the horizon. The fix was dropping the slot and forcing vacuum. The lesson. Alert on inactive replication slots within minutes. Not days. GitLab. 2017. Symptom. Massive table bloat after a schema migration. The migration touched indexed columns of every row in a hot table. None of the updates were hot. Indexes ballooned. The fix was pg_repack on the bloated tables. The lesson. Schema migrations on hot tables need bloat-aware planning. Anonymous Fortune 500. 2022. Symptom. Queries 50 times slower than 6 months ago. The cause. A long-running BI job opened a transaction every morning and never committed until the next day. The SMIN horizon was held back 24/7. The fix. Set idle in transaction session timeout. Kill the offender. Vacuum caught up over a weekend. The lesson. The default value of idle in transaction session timeout is 0. No timeout. Set it. The pattern across all 4 cases is the same. Nobody noticed vacuum until it stopped working. By then, remediation was slow, painful, or both. The teams that never have these incidents are the ones with 4 boring alerts and the discipline to act on them. When a table grows too big to vacuum quickly, the answer often is not more tuning. It is partitioning. Partitioning splits a logical table into multiple physical tables, called partitions, based on some column. Usually a date. From the application's perspective, it is one table. From the storage and vacuum perspective, it is many small tables. Why is this such a win for vacuum? For reasons. First, smaller vacuum jobs. A 1 terabyte table split into 30 daily partitions becomes 30 33 gigabyte tables. Each one vacuums in minutes instead of hours. Second, parallelism. Multiple Autovacuum workers can vacuum different partitions simultaneously. The total vacuum time drops dramatically. Third, cheap deletes. Dropping an old partition is instant. No delete statement. No dead tuples. No vacuum. You just detach and drop. Fourth, visibility map locality. Old partitions get fully frozen and effectively never need vacuuming again. The disk is silent for them. The standard pattern is time series partitioning. Create a parent table, partition by range on created_at, and have each month or week or day become a partition. Old partitions get dropped when retention expires. This pattern works for events, logs, audit trails, metrics, and mostly workloads. Partitioning is not free. Cross-partition queries can be slower without good partition pruning. Each partition has its own indexes. But for any table over 100 gigabytes that does not naturally shrink, partitioning is almost always the right structural answer. If your monitoring covers these 8 signals, you will catch every vacuum-related incident before it becomes an outage. Signal 1. Dead tuple ratio per table. Alert when n_dead_tup divided by n_live_tup exceeds 0.25 on tables larger than 1 gigabyte. Signal 2. Time since last autovacuum. Alert when it exceeds 24 hours on any table that takes writes. Signal 3. Transaction ID age per database. Run select age of datfrozengsid from pg_database. Warn at 1 billion. Page at 1.5 billion. The database refuses writes at about 2.14 billion. Always know how much runway you have. Signal 4. Oldest backend SMIN. The minimum of backend_SMIN from pg_stat_activity. Alert when its age exceeds 100 million XIDs. Signal 5. Long-running transactions. Now -zact_start. Alert at 5 minutes for OLTP systems, longer for analytic. Signal 6. Inactive replication slots. Anything in PG_replication_slots with active equals false for more than 10 minutes triggers an alert. Signal 7. Prepared transactions. Any row in PG_prepared_zax older than 5 minutes pages someone. Signal 8. Vacuum lag. Tables where dead tuples exceed the trigger threshold but no vacuum is currently running for more than an hour. This catches lock contention and cost limit starvation. And put the all-in-one health query on a permanent dashboard. The percent to emergency number. 50% means weeks to act. 90% means hours. Above 95%, it is all hands on deck. If you do these things, you almost certainly will not have a vacuum-related incident. Organized by cadence. Continuously. Autovacuum is enabled. Alerts on idle in transaction longer than 5 minutes. Alerts on inactive replication slots. Alerts on dead tuple ratio over 25%. Idle in transaction session timeout set to a sane value, like 5 minutes. And a permanent dashboard for transaction ID age. Those 6 items running automatically catch the vast majority of incidents. Weekly. Review the top 20 tables by dead tuple count. Look for anomalies. Check tables where last_Autovacuum is stale and figure out why. Watch pg_stat_progress_vacuum during peak hours to see if vacuums are completing. Review the top 10 hot tables. Confirm their per table Autovacuum settings still match their write rate. Check the hot update ratio. If it dropped, schema or workload changed. Monthly. Check age of datfrozengsid per database. It should be well below 200 million. Run pxtatuple on critical tables to confirm bloat is not creeping. Plan reindex concurrently for any badly bloated indexes. Review WAL archive health. And here is the controversial one. Actually test your restore from backup. Every month. Many teams have backups that have not been tested in years and will not work when needed. Architecturally. Set fill factor below 100 on update-heavy tables. Avoid indexing volatile columns. Partition huge append mostly tables. Maintain per table Autovacuum settings on your top 10 tables. And document and rehearse your vacuum full or PG_repack runbook so that nobody has to invent it during an incident. Operational discipline is not exotic. It is just consistency, applied to boring details, week after week. 8 ideas to take home. Memorize these. 1. MVCC is the cause. Postgres never updates in place. Every update and delete leaves a dead tuple. Vacuum exists because of this design. It is the cost of lock-free concurrency. 2. Vacuum and vacuum full are not the same thing. Plain is online and routine. Full is a blocking rebuild that causes outages. Use PG_repack instead of vacuum full, almost always. 3. Tune scale factor per table. The default 0.2 is wrong for any table over a million rows. Lower it to between 0.02 and 0.05 on your hottest tables. Single highest leverage tuning action available. 4. Wraparound is real. Vacuum is not just about performance. It is the only thing standing between your database and write refusal. Monitor age of datfrozengsid every single day. 5. Watch the SMIN horizon. Long transactions, idle and transaction connections, inactive replication slots, and prepared transactions silently disable vacuum across the entire database. Alert on all 4. 6. Hot updates matter. Drop fill factor on update-heavy tables. Avoid indexing volatile columns. The savings on indexes are enormous and largely invisible without measurement. 7. Monitor the 8 signals. Dead ratio, last vacuum, XID age, oldest backend SMIN, long transactions, inactive slots, prepared transactions, vacuum lag. 8. Partition huge tables. Drops are instant. Old partitions freeze and stay frozen. For tables over 100 gigabytes, this is almost always the right structural answer. If you take only those 8 ideas with you, you are ahead of 90% of operators. Vacuum looks like a maintenance chore until you understand what it is actually preventing. Then it looks like the most important background process in the entire database. Get it right once. Set up the right monitoring. And it disappears into the infrastructure where it belongs. Get it wrong, and it will eventually find you. Usually at the worst possible time. Usually with no warning. The most valuable thing you can do after watching this video is run one query on your production database. The all-in-one health query from slide 19. Run it. Look at the % to emergency number for each of your databases. If you do not like what you see, you now know exactly which slide tells you what to do next. If this video helped you, hit subscribe. There is more like this coming. Drop your worst vacuum war stories in the comments. They help everyone. And as always, try every query on a copy first, especially anything destructive. Vacuum is not optional. It is infrastructure. Treat it that way and your databases will quietly hum along for years. Thanks for watching.